Just letting the last few people kind of straggle in here. We normally hit right about 50, so we're just going to give it 2 or 3 more minutes. Jason's queuing up here. Jason, if you want to start sharing, you can. We, again, will be recording these. As we get people kind of flying in here, as always, myself, Emily Malin, my counterpart, Mustafa Hassan, we are the consultant specialist. It's a bummer that I already started the recording, so we have that forever, friends. That's good. We are the consultant specialist for Delta Controls. We are able to give you these presentations for CE credit, should anybody want them. We have 2 more to go today in our Blitz. This one is going to be around artificial intelligence and controls. And then our last one of the day will be about kind of that overarching building wellness, some of the codes that we're seeing in our industry that promote energy awareness and just building health in general. We're waiting on just a couple more folks to come in. I know we had a few that were signed up for this one particularly that weren't signed up for previous ones. And just with all of our technical difficulties, we had kind of truncated our breaks to make sure that we didn't have that today. So we're just going to give it maybe 1 or 2 more minutes, and then Jason's going to start us out. We will finish up with the building wellness one. We'll start that right at 4. Just because we weren't sure how much time we would need between breaks. And so that is what is on the schedule. So we'll do that one right at 4 p.m. Eastern time to get everybody finished up and out of here by 5. So we'll give it 2 more minutes, Jason, and then we'll get started. Just a reminder too, everybody be thinking about your most difficult and crazy AI questions to give to Jason. The crazier, the better. We want to hear them. So if you got any, he's ready.
Oh yeah, I spend way too much time thinking about this stuff.
Or is it just that everybody else doesn't spend enough time?
There's ballots somewhere in the middle. Definitely.
Probably. All right, we're getting up there, so hopefully we get a few more stragglers coming in. But like I said, Jason will be the one that is taking us home and through our artificial intelligence presentation. Reminder to everybody that we are recording all of these, so that way we can send them out to you guys afterwards. We'll give you the presentations as well, and you should be good to go. So without further ado, Jason, take it.
Awesome. Thanks so much. So yeah, this is a presentation that I initially presented at the ashrae Winter Conference in Chicago earlier in the year. I modified it a bit to kind of provide a bit more of a precursor, and because I had 30 minutes or 40 minutes or something, it varies, rather than 20 minutes. So I was able to kind of take more time and introduce the content a little bit better. Yeah, here's all the AIA stuff. I don't know how much I need to go into what we're doing here, but you're going to learn about AI in BAS, basically, and some things you can do with it, how it can kind of be enabled, what we could do today and what we could do if we met some prerequisites in terms of interoperability, particularly semantic interoperability, which I will go into some depth on in this presentation. So yeah, this is an overview. I'll skip this because you're going to see it all. So I always like to start with what is artificial intelligence. A lot of people have different definitions. I like to at least make that clear at the beginning of the presentation what I'm talking about, right? So artificial intelligence generally is considered the ability of a machine to imitate human behavior. This is pretty qualitative in terms of ways to evaluate this. One metric, an early metric, and still a metric people always talk about when they get into these AI debates is the Turing test, coined by Alan Turing, which is the ability to fool a human into thinking that the machine is a human 30% or more of the time, which is a fairly low threshold, actually, particularly with what kind of is floating around in the world today of what would be considered artificial intelligence. Now, within that, machines can imitate human behavior or thermophysical behavior or other things through machine learning, which again is a mirror of something, right? In this case, you'll feed it data and it will build some sort of a relationship, usually a line or a really complicated series of lines that can then be used to model systems. When you get deeper into this, you have deep learning. And what differentiates deep learning from machine learning is this idea where you're usually using a neural net-based model. What is a neural net-based model? Well, it's based on the idea of having an input and a nonlinear function to imitate neurons firing in the brain. So when you're using these, you're able to model very nonlinear problems and fit something to the data that is reflective of the data. You run into all sorts of issues with this, like overfit, poor accuracy, but in general, that's what deep learning is. So you kind of get into like these heavy mathematical functions, and deep learning's in a lot of these transformers, like what you see in like ChatGPT. So history of AI. Back to what I talked about in the last slide, Alan Turing test. John McCarthy coins the term artificial intelligence. You have a bunch of stuff that happens in the sort of second AI boom in the 90s, where if you remember, Deep Blue tried to face the world chess champion. Gary Kasparov thought there was a human in there, right? It was very exciting at the time. But of course, these all kind of move cyclically. We started ramping up again through the 2010s. Lots of stuff kind of starts to sound like a human, take in human data. People are putting a lot of money into this stuff. You start to see the ability to leverage data, which is a very data sciencey thing, to influence outcomes, right? Which is ultimately machine learning, really, but AI, if you're really fooling people into thinking it's a human. Then you get further along, you have things like ChatGPT starts emerging. And this kind of stops at 2022 because after that, like we're in what I consider kind of the state of artificial intelligence now, where really the big thing was when GPT 3.5 came out in 2023. In my opinion, that kind of changed the world. And everybody brought out their own large language models, and it got very exciting very quickly. And now I don't know what the best large language model is because it's hard to keep up. It really kind of follows a cycle, right? The booms or busts, right? They'll kind of follow a generic cycle. And here's some other technologies on here, which is kind of interesting. You see things emerge with innovation triggers, different artificial intelligence tools, artificial general intelligence. This is that weird one where you think it's really a human. I'm not optimistic that's going to move very quickly. But who knows? Like every 20 or 30 years, we get kind of a breakthrough that's hardware based. And here you have generative AI, which is like your large language models. When I started giving this presentation, it was kind of up here, and we're starting to move into the trough of disillusionment, right? Cloud AI services. I think a lot of people are disappointed because there's a lot of configuration, right? And I'll get into why there is a lot of configuration and how you can fix that later. But the key to this, really, in my opinion, is knowledge graphs, right? This idea that you have a a map of the system that contains knowledge of the relationships of everything. And it's distinctly different than a relational database because it's not necessarily one-to-one. It's not really table-based. It's more loosely structured and built on the idea of relating things, which I'll go into deeper in this presentation. So AI booms and bust. I think we're probably in the third one right now. The first one was like the beginning of computers, back when bugs were literally bugs. So you would pull a bug out of a tube. That's your bug. That's why your computer didn't work. There was money that was coming out of World War II, lots of money going to universities, national labs. Then interest ended a bit. People were like, how are we going to scale this? You can't, because only universities could afford computers and have the space for it, and national labs. So they get the boom to personal computing, right? You got your lug-along laptop thing. Eventually, things that are a little bit more portable. But of course, that kind of hit a bit of a wall once we started to see the limits of individual processors, right? So now everyone can have a computer, but you don't really have the computing power to make these big, crazy deep learning models. So you're limited primarily to expert systems, heuristics. Think kind of modern day typical analytics where you have a rule and you pass the threshold and it does a thing, right? You're able to process that data quickly. You're able to scan against these thresholds, and that's not a problem with these systems. But if you want to build a really big, complicated model with multiple inputs, not so much. Now we get to boom 3, video cards. Video cards got incredibly expensive because it's good for AI, and it's also good at mining Bitcoin. So everyone gets excited about this. You look at other companies out there like NVIDIA that makes these video cards, and their value has gone up incredibly because you're seeing so much more use for this, because you get through this threshold of the single core processor by parallelizing tasks heavily, and now you have so many more different little processors in these video cards that you can hit what the goals were for compute in the second boom now with the hardware we have. Of course, there are limitations to the techniques. I think we're starting to see, the arrow go down on this boom a little bit. So some modern artificial intelligence applications here. You have translation engines. Google wrote a really interesting paper on this stuff around 2017. And well, I guess I'm not supposed to say Google. A large company that does a lot of data research. Translation engines tended to get a lot more accurate around 2017 based on this, because now you have deep learning underneath, which was used before in translation engines. But they wrote this paper called "Attention is All You Need" that talked about putting what's called the attention head mechanism. Don't worry about the details of it right now. But putting that on top of a deep learning system, so now you can retain memory a lot better. So instead of putting in a sentence and you got to kind of keep it under 20 words or else it messes it up, you can throw entire essays in there. And these translation engines around 2017 got a lot better, and now you're seeing a lot more capability there, which is very, very exciting. You also get into things like stuff that assists you on driving vehicles. Think of things like lane keep assist, lane departure warning, adaptive cruise. That's stuff that has a machine learning model in it, because it's taking in the data of the road through a camera. It's trying to find the lines. It's trying to find the center line of your car and keep you moving on your way and not crashing into stuff, hopefully. Large language models now can write essays. So you give it little prompts, you give it ideas, it'll write you an essay. It might not be a very good essay, but it's something to start with. And these systems are still a reflection of the data they're trained on. So when you have these large language models that are embedded within a lot of these chat bots, think like ChatGPT, Llama, things like this, they are trained on the data that scrapes off the internet. So they're trained off of essays that already exist on the internet, which is going to be whatever it is. And I'll get into more generative AI disclaimers later. So you could do this now, but you need to kind of be careful when you do this. Also, this is one of my favorites. Now you can generate code with Copilot systems. And this can go a long way if you know how to do good prompt engineering. Historically, data scientists in the software development world are kind of considered very, very poor programmers. So this has at least helped me a lot to, mask my data science problems with my code and being able to make something that works a bit better and is formatted more consistently with, how the rest of the world does it, which is reflected in this. So kind of getting into the problems of why we can't scale artificial intelligence. Interoperability is a big problem. Step one is protocols. It all has to be on the same thing, right? So we have two buildings here. Building A was built in 2011. Building B was built in 2018. Building A had a lighting system that claimed to be a BACnet lighting system, but it only contained a BACnet system level controller, and it didn't route traffic through, so you couldn't actually see on BACnet things like PIR detection on the lighting system. You would have to go down to a computer in a basement, in a chiller room that's got a refrigerant leak alarm and all this other stuff. Absolutely miserable. So you can't get the real-time data kind of from a central workstation here. And this was, in my opinion, a big missed opportunity on this building. Research that was done there afterwards had to put in a separate standalone system with loggers to get the data. So that was kind of unfortunate. Flash forward ahead to 2018 with this other building, fully integrated lighting on the building automation system. You could do a fair bit more with this system because you could share the sensors between the lighting and HVAC applications. And both of these actually were labeled quite well in this case, but this isn't necessarily the norm in the field. The sensor density went up quite a bit, so you would have less area per sensor, which is kind of nice. So you're getting more data. Building B, part of it was actually intentionally highly instrumented for research applications as well. So a lot was kind of learned from this to this in terms of institutional buildings. But this is just step one, get it all on the same network, speaking the same protocol. So why can't we scale AI right now? Why isn't AI everywhere? Why can't you just talk to your building automation system and be done with it, right? Custom-made systems, everything's kind of bespoke. There's not kind of a set mapping that people have subscribed to and committed to at an industry-wide level. There's systems out there, which I'll talk about later, though I think are promising, and I have thoughts on where people should be committing their system mapping and labeling. Complicated fragmented systems. That's always tricky. You have different pieces here and there. You'll have a PC in the basement that's not really connected to anything. Proprietary systems, there's a lot of protocols out there that you can't even read with a third-party system. That's a big problem. Sensors getting disconnected, sparse data. You have a lot of gaps, and this is pretty common. It goes hand in hand with kind of modern networking, physical networking, because networks will go down, you'll lose samples, stuff like that happens all the time. Multi-client processing requirements. You have all these different services that go back and forth, and you have different clients using those services, and it becomes complicated managing everything in access. It's difficult to explain artificial intelligence to non-experts, specifically non-technical folks, and IT is always a question because a lot of these are based off of cloud services. You can host a lot of them locally, but things like OpenAI, for example, they don't release the model to be hosted locally. So if you want to use that, you need to interact with the cloud, and then you have to deal with IT. We're seeing more and more guidelines to normalize systems and processes. This is good. I'll talk more about this. Cloud compute allows you to not have to build a huge rig to handle everything. You can instead use what you use or pay for what you use. New LLMs, breakthroughs in that, that's been a big deal. There's a lot of stuff that we can do now with these new large language models that we couldn't with the earlier ones going back to like ChatGPT 2 circa the late 2010s. And kind of, on the flip side of, the complications of IT integration, people are starting to become more and more competent with respect to IT and security. Because when you're integrating with these systems, you have to know what you're doing, and you're always inevitably going to deal with IT in some manner, even if you're segmenting the system as an operational technology, OT system. Still, at some point, it's probably going to interface with the web and become an IT thing, and you have to know how to do that. And to interface with large language models and AI tools, really, it's not a lot different than going through an IT system, in my opinion. So semantic interoperability. I always like to roll this out because it sounds kind of nice. The four S's of semantic interoperability, and one of them is semantic. My apologies, I use it again. But the first thing is system. The number one thing is you have to get it all on the same network, the same protocol, so that you can see the data. And I got so frustrated about this that I wrote a paper and presented ashrae on this, about how you're really limiting what you can do if you're not doing backnet. And it feels like this should be, well, maybe not even necessarily backnet, but one protocol, right? At least something that's, open and third party friendly. That's important. And there's a lot of lost opportunity when you don't do that, and gateways become a problem and things get locked in, and this is a whole other kettle of fish. Syntactics, and this is where we've seen a lot of progress. I use the word ontology here. Don't worry about that too much, but this is what we call these things. They're essentially just dictionaries, right? Ontology being the study of what is, essentially. And what that really means in layman's terms is, how do things relate to other things, and what subclasses and superclasses do you have of those things? And then it's standardized in a dictionary. Then you can apply this dictionary, and everybody's building these knowledge graphs under the same concepts and the same classes, and it becomes interoperable now because you're not making up stuff, right? Of course, there's going to be some limitations when you do this. Most of these ontologies are extensible, meaning you can add things, and there's a set methodology to doing it, with the intent that if you do this, you could begin to contribute it to the main library if you wish, right? And this is where things like BRIC and ashrae 223p come in. Structural. This is an open problem. Where do you store this data? How do you store this data? How do you segment this data? Right? This really hasn't been answered by anything. There's been some initiatives through ashrae that have kind of gotten close to it, but they stay away from semantic web, which is knowledge graph ontology stuff. They kind of focus on tabular data, right? Where a schema is just a table, right? Not this more complicated thing. So that's a bit of a lost opportunity, in my opinion. But I think moving forward, we're going to have to tackle that a bit, or someone's going to have to demonstrate how to do this well, and it'll probably become a standard or something. So this will be interesting to watch. And that's kind of the next step in the research space. This has been in the research space. It's becoming more real and applied. This has been around forever. Well, not forever. It's been around since the mid-90s, right? Or sooner if you're not talking backnet, right? Protocols that other people can use. This needs to be done. This may never be done. Semantic context, right? And this image over here, I think, kind of highlights what this is. What is a plant? When you mention plant on a project, and this could be a district heating plant, or it could be plants in a green wall. However, by the time you get there, hopefully all the other data associated with gives appropriate context where you aren't confused. But no matter what happens, things can have double meanings if you aren't careful. And a lot of these ontologies try to avoid that, but you'll still have some stuff where that happens. So there's a lot of different things. When we talk about ontologies, really, I think we mean libraries, right? And there's a lot of libraries available that have standardized labels for things to name and classify them. Then after that, you could give it a proper name of whatever you want, right? In a lot of cases, people will take haystack and apply haystack or pseudo haystack to the backend object name field as a way to sort data in a building automation system. This is good. This is certainly better than 8 characters of ambiguous meaning, which I've seen a lot of that. I've had stuff roll across my desk in the last week that talks about systems like that, and hopefully we see less of that in the future. So we'll see how that goes. I'll answer questions at the end, just as it is up there. I see it, but I didn't read it because I want to keep rolling. Once you get into kind of less marker based where you're putting things together, you have things like brick, which is harmonized with real estate core. And the origins of brick actually come from haystack. So one of the founders of brick, I guess all of the founders of brick, but one of the founders of brick that's still around on this, Gabe Fierro, um, he has mentioned that brick was essentially meant to address a gap in haystack where you would have common sets of markers, which he calls tag sets, which would be its own individual thing. So let's say in haystack you have like supply, air, temperature sensor. That would be like sup, air, temp sensor, right? Now with brick, what you would do is you would do supply underscore air underscore temperature underscore sensor, and that's its own class. And if you look up brick ontology, brick schema online, you can look at all this. There's an interactive viewer to kind of see how that works. But the idea is that each class is its own unique thing, and the order of the tags in the tag set is also important. You have things like the GSA appendix, which uses the object name again, and its own abbreviations for that are floating around. The ontology alignment project, which is another sort of semantic web-based thing that's out of California. BACnet has been serialized in semantic web graph format. So BACnet and KNX, both of those you can use in a resource description format if you wish. Also, you have emerging ashrae 223p standard. So what is this? It started as a collaboration between Haystack and Brick, but really grew into much more than that over the years. Hopefully it gets released soon. It hasn't currently been released, hence the P for proposed standard. But this gets into much more granularity than Brick. So I think realistically, where in Brick you have a class like VAV blocks, 223P has different subcomponents, like you have single duct terminal unit and then damper and all these other pieces that would comprise a VAV. And I think how that's going to have to work is you're going to have a VAV container that contains a bunch of these things, and then that's going to be kind of copy paste and label and all this other stuff. So this will be an interesting one to watch in the future. For now, my recommendation is to go with things like Brick because it provides you the best context, but storage in modern systems is not really geared for this. So it's got to kind of be stored in different ways, and I'll get into that a bit. So why are we doing all of this, right? We're down this rabbit hole. You got all these dictionaries. You want to represent the data from a building in a way that lets you map the control system to the real physical assets and what you're trying to, control. So you can get a lot of information from BIM architecture and equipment schedules. Optical character recognition has come a long way. You just roll this into stuff off the shelf and digitize it in text format from a PNG file. Less so for drawings like this. They're kind of too busy. There's too much stuff on it. But ultimately, you want to represent the physical I/O and the physical systems in a way that the control assets that manage the equipment assets can be understood in how they relate. So all of this semantic web stuff is based off of the concept of a triple. So it sounds a little crazy, bear with me here. Tuple, two things, key value. Triple, three things. Subject, object, and predicate to link them together as a relationship. A very simple example here is a VAV class of object has point occupancy sensor, right? These would have proper names to be classified, but this is kind of the general idea, right? And you build a bunch of these and they recursively go up where your air handling unit is going to have part or it's going to feed VAV, and you get these graphs, which I'll show you a very simple example of shortly. So BACnet has tried to address this a bit. When BACnet addressed this was before a lot of the semantic web stuff was out there. I think the only library that was really seeing a lot of relevance in the field was Haystack, and at that time, tuples was more than enough. So what they have added as an optional BACnet property in 2016 is the BACnet tags field. And I've tried to put together a sort of visual schema to demonstrate how key value pairs could store subjects and objects, and then the predicates could be inferred based on the data that's stored at the point level tags field. So what all this means is this is basically an array, right? And you have your point name, which that's kind of a given property, but really something that's a little bit more indicative of this is your key is going to be equipment name or type, and your value for that is going to be wall thermostat 1, assuming you're indexing your wall thermostat. So it could be a more complicated way of, labeling it. It could be linked to the room or something, or the controller ID. But the point is that this is going to be kind of a proper name for that piece of equipment, in this case, wall thermostat. And then once you have all of this and map it like this, you can start to reassemble it and build out the triples. And this is nice because you could store all the semantic metadata in a table and then use pretty basic Python scripts or whatever your scripting language of preference is to reassemble the triples with RDF libraries. So a lot of complexity here. One of the big problems is you're trying to stuff a triple in a tuple, and you simply can't do that directly. You need to store more information other places. So I kind of thought I would make a JavaScript GUI to be able to interface with the BACnet system. So you have some BACnet point IDs here with your site, your device number, your BACnet point type, and your BACnet point index, point name, and then assigning all these different classes to it that can then be used to build out this type of a semantic web model just for a VAV that happens to be located in the hallway. And you can see how all this different stuff relates. And ultimately what you get here is you get a map between the assets of the real world and the BACnet object information, which gets kind of exciting because now you can start to map everything together. And whatever you call it, whether it's DAT, RMT, HUSAT, none of this matters anymore because you have classes that are normalized, they're in a dictionary. The human and machine know clearly what it is. The ambiguity of the object name field is no longer a problem, right? And that's really where all this is trying to go, because this needs to be understandable by essentially a human that doesn't have a lot of knowledge of automation systems, which is really the same as an AI machine, right? And if it's human readable, natural language, large language models can now read it as well. So kind of starting at the bottom on AI applications. And this is without having the semantic data model, semantic interoperability framework, which is a lot of overhead and it's a lot of work. And I spent a lot of time trying to figure out how to get this to work in the real world in a scalable, deployable format. Before we do this, if you have static I/O devices where your PIR sensor is at the same address, you know what it is. You can tag it or hard code its address in the algorithm, and all these other sensors. Now you can start to do stuff because you don't have to try and figure out where the sensor is. You don't have to try and figure out the scale, the type of sensor, because each of these little chips that goes in and does these sensors has its own quirks and non-linearities. But here's an example where you're going to have a sensor cluster on the ceiling. And in this case, it's reading temperature, humidity, luminosity, motion, and sound to fit a deep learning model to estimate occupancy count, which would normally have to be estimated with something like a camera, time of flight, Wi-Fi, stuff like that, where there's more privacy concerns. All this stuff, especially considering the sound never leaves the board. The sound's really just a sound pressure thing. It's not recording anything. Enables a higher level of privacy and kind of gives you the same sensors you would usually use to control a room anyway, if you have integrated lighting. So in this particular study, the main metrics that were used to evaluate the validity of the model were mean absolute error and the persons within two, which is exactly what it sounds like. It's the percentage of time where the estimate of the occupants using these inputs instead of something more complicated and privacy invading, estimated within two of that ground truth. So as you can see from some data, most of the meetings are 6 people or less. You have a fairly small fraction that becomes bigger. I think that this is pretty normal. Meetings that become larger than this kind of become more of a town hall or a hybrid online. And meetings of 1 isn't really a meeting Well, here it is. Yeah, but you have some of that as well, right? So 2 to 4 is kind of the most common of what you'll see in a room, and it's still fairly accurate with that, this particular machine learning model. So when you look at this particular set of samples, it was always within 2, mean absolute error of 1, and the persons within 2 metric becomes irrelevant at 1 person because it overrides that as just reading 1 or more as soon as the PIR sensor is triggered, because you triggered it to see that there's something in there, and then it tries to quantify the volume of that something, right? So as far as I know, this is already in the field. There's a lot of these in the field. So this is very real, very realistic. And sensor fusion can be done on static I/O address unitary devices, right? And this is a very exciting application already. Alarm flooding. I have mixed opinions on this. I think the only way that you're going to be able to do real alarm suppression requires some machine learning, but I think there's a lot of value before you get there. That said, let's first define what an alarm flood is. So ISA 18.2 defines an alarm flood as 10 alarms per 10 minutes per operator. So let's assume you, watching this right now, one person is an operator. And this is my favorite trick question of this presentation. Which of these 3 images is an alarm flood? The answer is all of them. So this one is 10-minute intervals with the alarms for 10 minutes. You see a lot of spikes on this. This is data from a real site. This is some alarms from a real site. There's 11 in this table. And this is 36 alarm bells, which let's say 1 bell per alarm. So this is 3 visualizations of alarm floods. So how can you manage all of this? Honestly, for most applications, you get away with kind of basic reporting, and this is heuristics. This isn't really what I would think is, the AI that people are getting excited about. But you could do a lot with this. And I think what I want to illustrate with this example is AI should be the last tool that you use before, and before that, you really want to use kind of more basic things like rule sets, or simple visualizations that just read the data, anything we know with visual inspection or comparing 2 numbers, right? And there you can look at sort of your average hourly alarm rate by month, the severity of the alarms, the performance today. This was a pretty floody day. Now, when you want to get into suppression, this is where the machine learning comes in, where you have to look at sequences of alarms, the similarity of those sequences, cluster those similar sequences, and then look at how those similar sequences relate to other similar sequences. So it's similarity scores all the way down. Kind of how this particular study was presented was with a dendrogram, where you have this non-dimensional threshold that you tune to either get a lot of different distinct floods or less, let's say 3 here distinct floods that have a root cause. So how all of this would work is you find all of the alarms that have similarity indices that are close, right? You bunch them together and you put a root cause on that flood of alarms. And then once a similar flood appears, you could then suppress that, or at least suppress the alert to the operator. The whole idea behind this is you don't want to overwrite the alarm queue. There's always got to be something that records the alarms on a site so you can do forensics later. But things that pop up on the screen are going to be a problem. And if you put too much, as was talked about in the earlier BAS 100 series sessions, people are just going to go. People are just going to answer calls, and alarms are going to be kind of meaningless. And I know a site that I work with that doesn't even spec more than like 1 alarm per device. There are more on air handling USB down to like the VAV level, and there's no alarms anymore because they just assume that they're not going to answer these alarms. So now we get to large language models. This is kind of what everybody's thinking is AI right now. It's very exciting. Translation engines, again, are kind of like the big thing that drove it, but then everything just kind of moved even more forward from there, and you get these chatbots and multi-agent API frameworks and GPTs and all these other acronyms. Don't worry about that right now. I like to give the generative AI disclaimer. This generative AI disclaimer was generated by generative AI. but it was pretty good. I mean, it's good at telling you what its problems are. uh, so accuracy, there's going to be issues with accuracy depending on the data that it's trained on. It can also hallucinate sometimes. There's going to be bias to the data it's trained on because it's a mirror of what has been exposed to. The user has to interpret the results, right? And this is why I don't think AI in its current form should be in the loop right now. It should be an assistance tool. It should be something that helps you make decisions and interact with the system, not something that actually runs the system. Because the reliability isn't there, and you have too much of this kind of random, what they call stochastic element to it, that's inherent with large language models right now in their current designs. And ultimately, the user is responsible for what they do with what comes out of the AI, right? So this seems self-explanatory, but you can't really blame the AI for what you do, right? Ultimately, you're responsible for what you do based on the advice of the AI, because the AI, you can't sue the AI, at least in the base form. And I put Plinko here from the Price is Right TV show because it's kind of like that, right? This is that stochastic thing I was talking about where, you know, you'll put an input in there and you'll get something a little bit different every time. And you can't really predict it because there's too many different layers in the middle that kind of morph what it was trained on into responding to what you want. And sometimes you hit 500, sometimes you hit 0. It's almost like talking to real people. Someone mentioned it at an ashrae conference I was at. So example here of a large language model system. What we did is we took the bot framework. It was a Microsoft thing at the time. GPT-4 Turbo, which was, in my opinion, the most accurate large language model at the time. But since a lot of stuff has emerged that's better, or at least comparable for certain applications, function calling framework, which is useful because you can build your own little functions to guide the large language model and supplement where it doesn't necessarily have the knowledge in its knowledge base. And then building data was communicated with via a BACnet API. So this is the first one where you really do need the semantic data model. Alarms, you can get away a bit without the semantic data model because typically alarm text and alarm settings will provide enough contextual information you can start to figure out what's happening. When you're dealing with a fully programmable system with I/O that can move all over the place, this gets crazy quickly, and this is where you need the semantic data model to know what you're dealing with. So in this case, the first prompt that came in, or the first question that came in was, give me the semantic data model information for room 451. So this was on virtual site. This was, which is a simulated site. This is a site where the controllers are simulated in a cloud service, and the I/O isn't actually connected to anything, so the values remain static as to what they were whenever it was created or loaded or whatever. In this case, they were stuck at a value, and you'll see what happens with this later. And you have the controller ID, you have the object type, you have the object address, and all of this gets mapped out with a semantic data model to link to this room, which was present in the object name, but isn't present in all the object names. And it gets a bit more complicated when you're dealing with specific sub-equipment. Somebody asked about the current temperature, returns the temperature, and that's accurate from an analog input object, that one. Then ASCII at the value an hour ago, and this is where you start to call functions. So in this case, it has to be able to access the buffer of a trend log object, which it can do. So it looks a few samples back at the trend log object and sees that the room temperature an hour ago in the trend log was 21.93 degrees Celsius. The temperature has been consistent. And this is where things start to get a little fishy. Then what is the current temperature reading of the thermostat in the room? This is a different one now. So the current reading is 22.12. There's too many significant digits, but that's just kind of the machine dealing with what was in there. Then this is where it gets really interesting. You ask it the record of the last 7 days, and kind of unsolicited, it starts to give you a fault report just based on what it sees, which was really cool. So it tells you the range of dates for which it has data, February 8th to February 12th, February 4. throughout these times, temperature readings were consistently logged as 22 point, the same value, right? So it starts to tell you ways that you can remediate this. And what was really exciting about using the large language model GPT-4 Turbo is this was the first version I was aware of where you could actually do file I/O. So we went with it here and asked it to generate a PDF report, which you see over here, and it summarizes everything and spits it out as a PDF file. You could ask it to format it too, but we didn't get that far. We thought this was good. And then advice for administration. Inspect the sensor. That's kind of obvious, but maybe not to someone that's new. Rigorous monitoring, maintenance schedules. And that also seems obvious, but it's summarized together with all of this. Then depending on the criticality of this sensor, redundant temperature sensors as a fallback option. So it's not bad for out of the box in how it assessed this. The fault detection wasn't a function. The function was to deal with the BACnet interface. So you get a lot of cool stuff out of it just with things that a large language model can infer from some data that you give it. So this is my last example of artificial intelligence. In this case, this is more of a machine learning thing. Is a field implementation of predictive control. And this is a study that I did for my PhD thesis. Obviously, I'm very excited about it. I want to kind of see it become more scalable. And I think really the missing link to this is the semantic data model that can allow for rapid configuration. So ultimately, what I was trying to do with this project is remove the unnecessary parts of predictive control algorithms and make it focus on just the data that's required to get close to the efficiency of the more complicated algorithm. The whole idea of this is you're stacking a bunch of models on top of each other. You predict occupancy. You get weather forecasts. From there, you start to predict how the space is going to respond because you've learned the thermal characteristics of the system, right? So of course, when you're trying to control space, indoor air temperature, and set point, the difference there is a big deal, and that's most of it, and that's why we have PID control loops. But in this case, this was a north-facing office. You would also have outdoor air temperature forecasts that are very important to this, and occupancy of the space an hour ahead, whether it is occupied or not. It was a 0 or 1. And the goal of this was 0 is to override the system and prevent overshoot. In this case, it was a 2-pipe VAV system. So seasonally, you only kind of have one option, and you would either overshoot or you wouldn't. And then 1 is business as usual. So you could just take the output of this and put it in front of whatever actuating algorithm you already have. So a bit about the facility. It was pretty highly instrumented: indoor air temperature, relative humidity, CO2 concentration, occupancy, even plug power current transducers. Return air temperature was ducted, and the return air was ducted, and we had temperature sensors in there. Illuminance sensors at 3 different depths in the space to understand daylight penetration. BTU meters on anything that had hot water flow through it. So we had it on the VAV reheat coils, as well as the radiant heaters below the windows. So this was a heavily instrumented building, so we could try and capture all the different energy flows and really truly evaluate the space. So from this, and I won't go into this too long, but the concept of meta heuristics. So these are the rules that govern the rules that I showed you earlier, where you're going to have kind of seasonal differences. Your set point is going to move in a different direction of the indoor air temperature on its natural drift with ambient conditions based on that. And then the idea that you want to kind of average out the energy that goes into the space over a period of time. And this is where you avoid overshoot, because you are predicting how much energy will go into the space in the future, and whether or not the energy that goes into that space in the future is going to cause you to overheat or overcool the space. I guess it would be energy going in, and cooling it would be energy removed, but you get the idea. So yeah, just looking at different inflection points and different jumps in accuracy. The goal of this was to try and make a meta heuristic that was not too complicated, but still was quite accurate, while shuffling the data to not overfit. So in a nutshell, lots of different scenarios of outdoor air temperature, humidity, illuminance as a proxy for solar radiation out of space. Don't worry about all this, but really the main point is uh, this particular study showed in the field that you could save anywhere from 20 to 40% of energy compared to a baseline of kind of normal operation when you do look at forecasts and put in forecast and predicted model data to respond to the system. And this is different because a lot of the other algorithms are reactive. Guideline 36 is reactive. Typical algorithms are reactive. PID loops are reactive because you're not looking at forecasts usually. Optimal start technically is not reactive because you're looking at weather forecasts and you're looking at some historical data to predict the future in terms of response to the building. But this really requires the semantic interoperability data model to implement because you need to know what all these different inputs are for this complicated algorithm and have them automatically connect with the data model. So yeah, summarizing it all up, a lot of forethought is required, right? Don't try to hit a fly with a sledgehammer, right? You need to use the right tool for the right job, and AI is the right tool for all jobs. It's cool, it's fun, but certain difficult applications require artificial intelligence or some form of machine learning or deep learning to handle these problems where there's kind of unique constraints. Scaling requires semantic data models. There's no way around this. You can get there a fair bit with things like Haystack, but there's still a human in the loop. My personal goal is to try to help move the industry towards not having to have a human in the loop for this mapping process, because usually the person that's doing the mapping has a lot of expertise and could be doing more valuable things than mapping data points. Single devices, you can do that now, but it's only on one device, so you can't group systems together, particularly with distributed control. And ground truth data, that's like a big deal. You need to have good data to fit the model too. So if you're trying to indirectly model something, you need to know that the data that you're fitting it to is accurate. And if it's not, you're going to get weird behavior. And it's the same idea as when a large language model chatbot hallucinates. It was fit to some weird stuff, and you're hitting that weird stuff now with bad ground truth data. So that's very important. And yeah, that's all I have for today on artificial intelligence. I'm happy to answer any questions anyone might have. I always like questions. I'll go to the one in the chat first, actually, though, if that's okay, because I've kind of ignored this for a bit. Ah, early 2000s projects. So this is interesting. So doing stuff at the device level is going to be hard. You're dealing with like probably V3 stuff. In our case, but really anything you have kind of around that era is going to be somewhat hardware constrained. So really you have to pull out the data. You have to be able to map the data in some way, as I mentioned. At least hopefully the naming was consistent. Maybe someone left a sheet of paper somewhere in a mechanical room that tells you what, T, underscore T underscore means, if you're lucky. If not, there are some tools that can start to do this, but you really have to be able to figure out the naming scheme and identify what everything is, and then bring all that data into a central location. But realistically, if you're looking at AI for those types of projects, it's probably going to be through supervisory control on some sort of computer or industrial PC, right? And there's also a fair bit of integration this time too, because tooling hasn't really come to the point that you can do all of this auto configuring. Right. So I would say if you are going to look at a project like that and it is a one-off, I would go to the effort of trying to build like a whole scheme to build a semantic data model for it and build a tool to do that. I think one-time bespoke modeling is good, but it's not going to be cheap. Right. In some cases, it's better to try and convince them to, recapitalize the project or something and put new devices in if they really want AI at the edge. Right. Any other questions?
Oh, we got a couple more in the chat there.
Yeah. All right, I'll do alarm floats first. Ah. Um, Okay, so this is complicated. So a bit of both. So you'll have what is kind of in the alarm management field called a chattering alarm, which I think is these bad alarm setups you're talking about, where just kind of the natural dead bands in a space will start to trigger alarms, and that's something where if you can just change like ranges or high values or low values or whatever in the alarm, that would go a long way to solve the chattering alarms that flick on and off all the time. In the alarm flood algorithm that I talked about, the first thing it does is it filters out the chattering alarms. Now, once you get to kind of multiple real alarms, that is a real thing. Say you're doing like a generator test or something, and you're flipping the power off, all the VFDs go down, you get like pressure alarms, temperature alarms downstream. Um, Very quickly, that does become a real flood, but you do tend to get a large volume of stuff that's just poorly configured, and that's a whole other problem. Um, and that could actually even look good during the commissioning process, but then over time, um, things drift, and you actually have people in the space, which changes the loading of the space and responds differently. So there's a lot of different things that can go wrong. The answer is both. Um, but I try to really focus on the real floods and not include chattering and bad alarm setups in the flood. I hope that answered that question. Feel free to throw a follow-up in there. Semantic modeling. Okay, so for now, really the object name field is what is best to work with. Optional backnet tags property is something else, but the interface with that is not fantastic right now. Things will improve in the future. As far as for now, though, I mean, honestly, you're probably going to get the most bang for your buck doing object name haystack, and then being able to up convert that later. But in the future, I think things are really moving towards doing native brick on the back end, where people won't even notice they're building a brick model. Well, they're going through their development workflow. But for now, as I mentioned in this, like a lot of these systems, we're just using the object name field here. Yeah, like this is object name. This is object name. Backnet is literally object name. So that's a good way to start. And then as we move forward, embedded semantic data models going to go a long way. Brick equipment data visualizer. So I actually visualized this. It wasn't my tool that visualized this. This was this was the Brick visualizer tool on the Brick website. They've since moved to something a little bit different. It looks a little bit different, but it's the same idea. This module, I can give it to you. I provide no guarantees it works well. It has a lot of bugs. It was made by a co-op student, which no offense to co-op students, it's great, but we didn't actually put it through software QA. So if you are interested, Jason, please email me, and I'm happy to kind of show you how it works and what we're doing with it, and how this inserts the data in the backnet tags field to kind of do this thing, sort of. Perfect. But I have lots of thoughts on this and things you can kind of do now with object name, and kind of I can give some guidance on where things are going in the near and less near term. So, are there any more questions? Perfect. Well, thanks so much, everybody. I'll throw my email on screen again if people want to reach out. Feel free. I'll respond as quick as I can. Sometimes things are a little crazier than others. But yeah, have a great day, and it was my pleasure to kind of join in as a guest on this series.
Perfect. Thanks, Jason. Yeah, and again, we've recorded all these, so we will be sending these out with the slide deck to you guys as well. With that, our last one is going to be at 4 p.m. Eastern time. We're going to go through final one, building wellness. It'll be a lot around some of these codes and where we're seeing things going, different certification programs, lead well, all that good stuff. So join us back here in about half an hour to finish everything up. Tell your friends. Thanks, Jason. We'll talk soon.